Resistance welding numericals. I will go a little bit fast because the time is short today. Okay. So for the resistance welding, we have got some formulas and parameters that are very important to consider. For the formula, the most important formula is that the heat generated H is equals to current square, which is I square, multiplied by the resistance multiplied by the time duration. So let's move back to the lecture. So the heat generated during resistance welding H is equals to I square R times T, where H is the average heat and the unit of energy is joules. I square is the current. R is the resistance. And T is the time. So the unit of current is amperes. The unit of time is seconds. And the unit of resistance is ohms. So this is the formula for the heat generated during resistance welding. And I can write the formula, rearrange as well. So when I'm going to rearrange, it will be H over T is equals to I square R multiplied by K. And this K is called uh, loss factor. This is called loss factor. Loss factor K is equals to heat lost by conduction slash radiation. K is different for different process. Different for different process. Okay. So this loss factor sometimes is assumed to be 0. Okay. So when losses are assumed to be 0, then K is equals to 1. That is why in the first formula, H is equals to I square RT. Okay, this is an ideal formula, ideal case. When K is equals to 1. So this is the ideal case. And this is the real or actual case. So the formula is, when we rearrange, then H over T is equals to I square R into K. And H over T, as you know, is energy, heat energy per unit time. Okay. So this is joules per second, and joules per second is called power. Power is the rate of doing work, means energy per unit time. So this is all. This is the only formula which is basically used for resistance welding. In the previous arc welding, if you have gone through the videos already, you guys should know that the heat generated required to melt the material, heat required to melt the material, that formula is H is equals to mu m into uh, what was the formula, into volume. Okay, so this is heat generated required to melt the material, and this is heat generated during the resistance welding operation, and that is dependent on the current and resistance. So this formula is process formula. Okay, and if you go down, this formula, which is heat required to melt a material, depends on the material properties. If you guys have gone through arc welding numericals already, then UM basically is specific energy. Specific energy is different for different materials. Okay, specific energy is different for different materials. So if you are going to open the lecture, okay, of the resistance welding, you go to the this lecture, and you go down, and you see, you are going to see this table number 30.2. In table number 13.2, the specific energy, which is mu m, is given for different materials. So it takes different amount of energy to melt different materials. This is what this table is saying. It this table is saying that for a unit volume, for 1 millimeter cube, for a unit volume, the amount of energy required to melt the material. So here you can see that the top material, which is easy to melt and which has the least specific energy, is 2.9, which is for aluminum and its alloys. Whereas if you go at the bottom, then here you can see that titanium is a material which is the hardest to melt, and we need a lot of energy to melt titanium material. So for aluminum and for magnesium, specific energy is 2.9, and but in terms of British thermal unit, magnesium requires 42 and aluminum requires 41. So the least is aluminum, followed by magnesium, and then titanium is the material for which the highest amount of energy is required. So this table is very important if you want to calculate the amount of heat energy required to melt the material. If you have, let's say, 2 millimeter cube of volume, then what you will do, H is equals to mu m multiplied by the volume, right? So you will multiply the volume multiplied by specific energy. So let's say if I say that what is the heat energy which is required to melt 2 millimeter cube of aluminum, then what you will do, H is equals to um multiplied by volume. So um of aluminum is 2.9, multiplied by volume is 2. So 2.9 into 2 is going to be 5.8. Okay. So this is how you calculate the amount of heat required to melt a material. And in table 3.1, we have got different types of material, and we have got different types of properties which are mentioned. Okay, so in table 3.1 you have got the density. Let's say I ask a numerical about copper and I don't give the density, then you have to refer to this table and get the density value. So in the question I can ask, okay, what is the how maybe there is something related to density, then you have to get the values from this table. So let's solve one numerical and then we will understand what I'm talking about. So this was the theory of resistance welding analytical numericals. Okay, it is already available, and do note that the value of K, which is the efficiency, also depends on the resistance of electrodes, electrode workpiece contact resistance, resistance of individual parts, etc. So K also depends on these kind of stuff. So let's move to numericals. Number one. So numerical one number one is saying that the heat generated in spot welding. So spot welding is basically a type of resistance welding where we basically produce a spot between two sheets to produce a join or a weld. So assume that two 1 millimeter thick steel sheets are being spot welded at a current of 5000 amperes over a current flow time of 0.1 seconds by means of electrodes which are 5 millimeter in diameter. Estimate the heat generated and its distribution in the weld zone if the effective resistance in the operation is 200 microohms. So I know the thickness of the sheet, I know the current, total current, I know the current flowing time, I know the electrode diameter. So estimate the heat generated and its distribution. So we are required to ask two things. So for solving numerical, please do follow this step, which I'm going to tell you. You should follow this step so that I can give you marks structurally. Remember, in the first class also I said you should uh, always attempt all numericals in the exam. Okay, so we have got problem number one. Problem number one. For problem number one, let's write number one heading, which is the most essential one, given data. Heading number one, given data. If you write this heading and you write the given data, I will give you 3 marks out of 10. Given data. So if you write this heading, then 3 out of 10 already. So what is the given data? Current I is equals to 5000 amperes. Time is equals to 0.1 seconds. Resistance R is equals to 200 microohms. Okay, and what else? 1 millimeter and electrode diameter is 5 millimeter. So we have got two 1 millimeter plates. So I've got two plates. Each plate is 1 millimeter thick. So this is 1 millimeter. This is 1 millimeter. Then I've got my electrode. These electrode have a diameter of 5 millimeter. So this is the construction or this is the given data. Now before I am going to solve the numerical, I need to write the assumptions. Because the process efficiency is not given, we are going to assume what? Assume K, which is the loss factor. Assume K loss factor is equals to 1 because the efficiency is not given. Now number 3, so you've got 1 marks for this. Then number 3 is applied formula. Applied formula is H is equals to I square R T into K. So you got now this is 4 out of 10, and then this is 7 out of 10 already. Then number 4 is solution. Okay, so solution heat generated H is equals to so we have got this resistance in micro ohms. So basically, 1 micro ohms is equals to 10 to the power minus 6 ohms. Okay, so my resistance becomes 200 into 10 to the power minus 6 ohms. This is my resistance now. So this is conversion of unit. So let's go back. H is equals to current is 5000 square multiplied by resistance is 200 into 10 to the power minus 6 multiplied by the time is 0.1 seconds multiplied by the loss factor is 1. So the heat generated due to the process comes out to be 500 joules. This is the answer. Now if you go back to the numerical, it is saying estimate the heat generated and its distribution. So basically by distribution it is asking. So part B, and this is part A. So what is distribution? Basically how much is the volume of the material. This refers to volume of material welded. So what is the volume of material welded? So you go back and see that the welded portion is this one only. So this is the welded portion. Okay. Because the electrode is circular, the welded portion will be circular also. It will be circular. Okay, and it will be 1 plus 1, 2 millimeters thick. This is the welded area. This is the welded portion or welded area. So we need to calculate the volume of this cylinder. So we need to calculate the volume of the cylinder. So volume is equals to pi r square into length. So volume is equals to pi t square by 4 multiplied by length. Now what is the diameter? Diameter is, I think, diameter is 5 millimeters. So volume is equals to pi 5 square divided by 4 multiplied by length. Length is 1 plus 1. So you guys can calculate what is the answer. Easy calculation. So this was part B, or the distribution of the weld. So you've got two answers here. Answer number one and answer number two. So we will move on to the next numerical. Question number two. So question number two is saying two flat copper sheets. So the material they have mentioned is copper. It means that maybe we have to refer to the table which I said already and earlier on, which is this table, the materials table. So maybe because they have mentioned the material copper already, so you guys have to refer to this table number 3.1. Okay. So two flat copper sheet, each 1.5 millimeter thick, are being spot welded by the use of current which is 7000 amperes, and the current flow time is 0.3 seconds. The electrodes are 5 millimeter in diameter. Estimate the heat generated in the weld zone, assuming that the resistance is 200 microohms. The specific energy of copper is 6.1 joule per millimeter cube. So here in this numerical, they have given the specific energy of this material. But let's say in the exam, I don't give you the specific energy, I give you this table only. Okay, this specific energy table. So you need to go and see where the copper is. So this copper is here. Copper is specific energy is 6.1. So you're going to take this value in the solution. So this is part A. And part B, calculate the temperature rise assuming the heat generated is confined to the volume of the material directly between the two electrodes and the temperature is uniform. The specific heat energy for copper is 385 joules per kilogram Kelvin, and the density of copper is 0.00897. So, for the purpose of solving in the class, I have written these values, but I will not be given these values in the exam. You have to get the specific heat and density of copper directly in the exam. So, you go to the table and you go and see for the copper the density is 8970. The specific heat is uh, 385 joules per kilogram Kelvin, and the yeah, so and the melting point is 1082. Sorry, not 1082 degrees centigrade. So these are the properties that you can get for copper. So let us write the given data, then we are going to write the assumptions, then we are going to write the what we call applied formula, and then we will solve the numerical. So let us go back to our answer sheet. Question number two. So number one is given data. So what was the given data? Current is equals to 7000 amperes. Time is equals to 0.3 seconds. So do note that the time for which the current is on is 0.3 seconds. So resistance welding is very fast that in 0.3 seconds it will produce the joint. It's so fast. Now we need to require to calculate the amount of heat generated. Okay, the resistance given is 200 microohms. Also given is the specific heat of copper. This is 385 joules per kilogram Kelvin. The specific energy required to melt copper is equals to 6.1 joules per millimeter cube. Again, you've got two copper plates. Copper is a little bit of goldenish in color. So you've got two copper plates. These copper plates are 1.5 millimeter thick. And then we have got the resistance welding electrodes which are touching these plates. These electrodes are 5 millimeter in diameter. And the effective weld volume or weld area is this one. So this is the weld volume. Okay, so this is the given data in the numerical. Now let's move to assumptions. Yeah, what is it is asking? It is asking us to find what is the required heat to melt the material and calculate a temperature rise. Temperature rise is delta T. So calculate temperature rise. Part B, it is asking what is delta T temperature rise. Okay. So what is the assumption? Assumption is that loss factor K is equals to 1. Then we will move on to applied formulas. What are the applied formulas? So the applied formulas are number one, H equals to I square R T K. Then formula number two is amount of heat is equals to melt the material is mu m multiplied by V. Then the amount of heat given to material is Q is equals to m Cp delta T, and volume is equals to pi by 4 T square into length, and density is equals to mass over volume. So mass is equals to density multiplied by volume. So these are all the formulas which are going to be applied in this numerical. If we go back and see, it is asking that uh, two flat atoms what estimate the heat generated in the weld zone. Okay. So what is the heat which is generated in the weld zone? Okay. So solution. So H is equals to I square R T K. So H is equals to 7,000 into 200 into 10 to the power minus 6 square multiplied by 0.3 multiplied by 1. So the amount of heat generated by the process is 2940. Let's say I ask you guys another part. What is heat lost? H lost. I ask you this mini question. What is heat lost? So you will say, so you first calculate the total heat. This is total heat. Heat by the process. Then you will calculate the total heat which is required to melt the material, which is mu m multiplied by volume. Okay. So volume is equals to I into 5 into 10 to the power minus 3 whole square divided by 4 multiplied by 1.5 plus 1.5 whole into 10 to the power minus 3, because we convert millimeter into meter. Remember that. So volume comes out to be 58.9 millimeter cube. So this implies that H is equals to 6.1 or 50, yeah, 6.1 into 58.9. Okay, so, okay, actually made a mistake, I think. So there is no need to calculate in millimeters because we want the volume in millimeters. So this is wrong. We want volume in millimeter cube because um is in joules per millimeter cube. So this is millimeter cube and this is joules per millimeter cube. So they will cancel each other out. So H comes out to be uh, 359 joules. What is this H? This is amount of heat required to melt the material. Okay. So what is the heat lost? Heat lost is the amount of heat generated by a process minus the amount of heat which is used to melt the material. This is my actual heat that I should use to weld or melt the material. However, I have to give how much? 2940. I am using applying 2940, but the amount of heat required to melt the material is 359 only. So the total heat lost, okay, is 2581 joules. This is the heat lost during the process. So this was a mini part that if I ask you what is the heat loss, then you can do this work. Okay, this was a mini part. Now let's move to part number B. In part B, it is asking what is the temperature distribution or temperature difference or temperature rise, delta T. So part B is temperature rise, delta T. So since Q is equals to mCp delta T, so first delta T is equals to Q over M into Cp. What is Q? Heat generated. So delta T is equals to H over M Cp. So delta T is equals to 2940 divided by Cp is 385 kilojoules per joules per kilogram Kelvin multiplied by the mass. So what is mass? Mass is equals to uh, density multiplied by volume. The density is given. Density given is 0.00897 kilogram per millimeter cube. I think the density given is 0.00897 kilogram per millimeter cube. So I go back and it is kilogram per millimeter cube multiplied by the volume was 58.9 millimeter cube. So the mass comes out to be 0.53. Uh, just a second. What is the formula for Cp? Cp is joules per kilogram Kelvin. Okay. For copper, it's 385 joules per kilogram Kelvin. So the answer comes out to be 0.00897 multiplied by 58.9. So 0.528 or 53 kilograms. Specific energy heat for copper is 385 joules per kilogram Kelvin. joules per kilogram. 31. One mistake. So the mass is 0.00897 grams per millimeter cube. So it's grams per millimeter cube. That's a mistake. This is grams per millimeter cube. So the answer is in grams. So now I need to convert mass grams into kilogram. So 1 kg is equal to 10 to the power 3 grams. So 1 gram is equal to 10 to the power minus 3 kg. So this is 0.53 into 10 to the power minus 3 kg. So putting the value of mass in this formula, so this comes out to be 0.00053. So delta T comes out to be 1400 and 14,400 kelvins. Okay. So we convert Kelvin into centigrade. So 14,000 Kelvin delta T comes out to be 14126.85 degrees centigrade. This is the extreme temperature rise which has occurred. From table, the melting temperature for copper is the melting temperature for copper is 1082 degrees centigrade. So imagine how extra amount of temperature has rise, 1082 degrees centigrade. However, the temperature difference is 14,000 degrees. So imagine how much amount of heat has been generated in a span of only 0.3 seconds. Okay, so this is the concept. How the heat is distributed and how the heat is generated during the resistance welding. I'm going to share this video. Okay, go through this video and see how the heat is generated during resistance welding and how it is distributed. It means how much is the extra heat which we are given, which are basically we are giving during the process. So because of this extra heat, extra amount of temperature is also increased during the resistance welding. So on your WhatsApp, okay, so I have shared a video. So this is the resistance welding in progress. Here you can see that as the temperature increases, the amount of heat distribution increases, but only in this pink zone, okay, in this pinkish zone, the melting is occurring. The rest of the heat is conducted and distributed. So we are putting a lot of excessive heat, and that excessive heat is lost during the welding process. We've got two plates. This is my electrode. We've got two plates, and then the between these two electrodes, we are applying current and voltage, and resistance is due to these plates and due to the fang surface. So the heat is generated during that process. So you can see that a lot of heat is generated. Some of them is lost, and only small part is used for melting the material. And the temperature rise is also very high.